Ja.
Ikke sant?
Det er for sent, da.
Det er already.
Listen, I fully appreciate that if you're new to sailing and you come aboard a boat, you go out sailing and wind is picking up and the boat starts heeling and it heels more and more and you feel uncomfortable. You don't like it. You're worried. You're scared even. And is it dangerous? So can a sailboat capsize? You've heard about that, haven't you? And of course, some can. Dinghies are capsize all the time. It's a part of the sport. It's a part of the fun, actually. But others, if you go cruising, is it how does that work? That's what we'll try to look into in this video. But I have to reassure you, if you're sailing a boat which is approved under the European Union's Recreational Craft Directive, Category A, and that goes for most production boats from 30 foot and upwards, you will be safe. So if you come in a situation as seen on these pictures, you'd better hold on. That's the most important thing. Welcome to the new YouTube Sailboat channel about sailboats, to the second video, which then is, as you understand, about stability. My name is Petter Mowinckel. I'm a naval architect. I've been sailing since 1969, and my wish is to give something back to the sailing community. So if you like this video, please give me a like and subscribe. Stability matters. Stability is one of the most important safety parameters of a sailboat. Stability determines what sort of weather wind you can take, whether you can do ocean crossings or that you have to stay inshore. A high degree of stability gives a more comfortable sail for the cruising sailor, but also a faster sail for the racing sailor. When you've seen this video, you should be able to understand what stability really is, also from the naval architect's perspective. And you will also understand whether a boat can capsize or not, because we will look into the fundamentals of stability. And at the end of the video, we will have a look at the CE regulatory requirements, which is the standards of EU, and hence applicable for a majority of boats sold globally. Now, since this is physics, let's recap a bit for those of you who dropped it out at school and get to know our friend Isaac Newton again. And he had some laws, and one of them is about forces and counterforces. So given that something, for example, a boat, is in a stable state, not accelerating, it could be moving at constant speed or standing still or heeling at a constant angle, every force will have a corresponding counterforce that yields an equilibrium of forces. So if you stand on your bathroom scale to see what yesterday's dinner did to your weight, you will push down on the scale, but in return that will push back up on you. And then you can see whether yesterday's dinner actually was as bad as you feared it was. And for example, if you're driving your car and you are flooring your accelerator, it will accelerate up till it reaches the top speed. And that's when the engine power equals the drag forces, basically wind resistance. So force, counterforce, that is number one. Secondly, this also goes with a moment, and a moment equals a force times a lever or an arm or a distance. And these must also be in equilibrium. So any moment must be counteracted by another oppositely directed and equally large moment. So, for example, if you play with your child on a seesaw and your weight is twice the weight of your child, then of course you have to sit at half the distance from the pivot. And the pivot itself will again give the counterforce here, which will then equal your weight plus your child's weight. So when we start looking at stability, I'm quite sure you'll recognize these principles. So here is our boat, and the boat has a weight that pushes it down. And this weight consists of the hull, plus the deck, plus the rig and sails, and of course the keel. And altogether this gives the weight of the boat, which acts in the center of gravity. And this center of gravity is then the average position of the total weight. And of course, it's very important for stability in general, the position of the center of gravity. Now, there has to be another force working the other way, according to Isaac Newton, and that is when Archimedes comes in. And Archimedes, he tells us that when a body is submerged in water, it experiences a buoyancy which is equal to the weight of the displaced liquid. And the center of gravity of this displaced liquid is actually where buoyancy acts. So that would be the counteracting force in this respect. And as long as there's no other forces acting on this, no moments, no healing moments, the center of gravity and center of buoyancy will be on top of each other. But then we go out sailing, and then we know, of course, that wind will act in the sails with a force. And again, according to Newton, since the boat doesn't go sideways but forwards, there has to be a counteracting force working somewhere else on the boat. And that would then typically, most of that would be on the keel, which is also a sort of a wing. And now there's a distance between these forces, and that makes the boat heel over, and that is then giving a healing moment. But since this boat doesn't heel further, there has to be an oppositely directed righting moment, which makes it lying there in a stable position. And this righting moment is actually what creates stability. Now, what happens here? Well, there is something you could have a look at here. You see there's an orange area and a green area. And when the boat heels over, you lose a bit buoyancy on one side, on the orange side, but you gain the same amount of buoyancy on the other side. And what happens then? Now, let's magnify this picture a bit. Remember, we lost buoyancy on the orange part, and we gained an equal amount on the green part. And that means that the buoyancy moves sideways. So when you're healing like this, the center of gravity and the center of buoyancy are not directly above each other anymore. You have now got a horizontal distance between the center of gravity and the center of buoyancy. And this horizontal distance is called G set. I mean, we understand why it's called G, that's gravity, B for buoyancy, why it's called Z. Well, I really don't know, but that is the naval architectural term for it. Now, G set is a righting arm. That means that G set times the weight of the displaced water, which equals to the weight of the boat, gives you the righting moment. The G set is thus a term which is very important when discussing quality. Now, what happens to G set if you continue to heel the boat over? Right now we're doing some good sailing, but if we, for example, broach something, we might end up here. And now we see that G set has increased further. Now we're actually very close to what usually would be the maximum G set, where we have the biggest righting arm. And if we continue to heel the boat over, like this, for example, if you're knocked over by a gust, you could end up here close to 90 degrees and still have lots of stability left. The boat will still come up, even if you're knocked down to this level. And if you remember the pictures I showed in the opening of this video, I said, hold on, and that is true, because the boat will come up again. But if you continue to heel the boat over, at some point, the center of buoyancy and the center of gravity will be directly over each other again. And at that point, you don't have any G set at all. You don't have any righting moment. You don't have any stability. it's time to get worried. Now, this development of GSET can be given as a curve. It's called the GSET curve, and that really describes the boat stability. And this is a typical curve for any modern cruiser between, for example, 8 meters and 50 meters, or 25 feet up to 50 feet, something like that. And we see that it rises steadily up to about 50, 60 degrees, and then it goes down again. And at 90 degrees, you still have quite a lot of stability before you come down to this point where their G and B are directly above each other again, and that is what you call the angle of vanishing stability. Now, I said this was a fairly standard cruiser, which in modern boats are quite wide. If you take narrower boats, for example, like old meter class yachts, they are not there at all. They are much narrower, and it's pretty easy to understand that if you have a narrow boat, it's a limited way how far to the side the buoyancy actually can move. So you'll have a smaller GSET and thus less stability. So you will heal more, and they do. Meter boats heal much more than modern boats do. Now, that's not so good, but on the other hand, you have a benefit, and that is your angle of vanishing stability might come up to 150 degrees, or meaning that this boat will be more or less self-righting. So let's pause a bit here and do a little recap of how far we've come. Now, the GSET curve describes your stability in the form of the righting arm, the lever, which again then can create the righting moment. GSET times the weight of the boat gives you the righting moment. Any modern type cruising boat would have a maximum GSET and maximum stability at around 50 to 60 degrees of heel. And it would also have an angle of vanishing stability between 150 and 130 degrees of heel. So what does this make in numbers? If we take a 40-foot sailboat with a weight of approximately 8 tons, the maximum GSET, again at about 50 to 60 degrees, would then be could be about 70 centimeters. And with that figure, that would give us a righting moment of 5.6 ton meters, which then again equals putting 2 normal cars on the railing of your 40-footer, which usually is about 4 meters wide. So quite big forces and the fruitful thought. Now, what is the biggest enemy of stability? We'll have a look at that. And then further in the video, we'll have a look at how can we improve stability further. What are the tools that the naval architects will have in the toolbox to make this even more stable? So don't leave me yet. Stability's worst threat is water ingress. If you get large amounts of water inside the boat, it will start running on and sloshing back and forth, meaning that you lose control of center of gravity and your GSET. If this free surface, as we call it, comes up, if you get so much water into the boat that it equates to the waterplane area of the boat itself, then there is no stability left from the GSET at all. When calculating this, the moment of inertia of the free surface is vital, meaning that the surface comes into the equation in the power of 3. Now, it's a bit nerdy, but this means that normal tanks, like diesel tanks or water tanks, the free surface in them would be so narrow that they will not impact this at all, but this is really the threat, the biggest threat to stability. And this does not only apply for boats like this, but also for ships. And some of you might remember the Townsend Tourism tragedy in 1987, where the ship Herald of Free Enterprise capsized. they forgot to shut the bow door, and since there's a big car deck, water started running freely onto the side. When it then starts heeling over, more water comes immediately, and it took only a couple of minutes before the boat was on its side, killing 193 people in tragedy. So be aware of much water in your boat. You wouldn't like that. I have to admit that was a bit depressing to talk about. I'd much rather like to talk about how to improve stability. That's much more fun. And what can a naval architect do to improve stability? And one thing is moving the center of gravity downwards. And I believe most of you have seen that there are some boats which have a bulb added to the keel. And of course, that brings your center of gravity significantly down. And the moment you start heeling, that will also benefit your G-set, as shown in this figure. So getting the center of gravity down is important. But then we can also think in another dimension, because a boat of 12 meters length, 40 foot, will usually draw about 2 meters, but the air draft might be 20. So that if you manage to save 1 kilo in the mast, that could give the same effect as adding 10 kilos in the keel, as a rule of thumb. So reducing weight aloft also gives you enormous benefits. And the lighter sails, halyard, avoiding furlers, and of course in-mast furling, which contributes significantly, and a lighter mast. So if you've got well-filled wallet, carbon mast will give you a totally new boat stability-wise. Secondly, we can look at the hull shape for better form stability. And that means that we're not looking at the center of gravity, but rather moving the center of buoyancy sideways. And by adding width, maybe through hard chines, as we see here, which is very popular, because then the moment you start heeling, suddenly you dip that into the water and it starts taking effect. So by having a greater width over a larger length of the boat, plus hard chines, that gives you a great increase in your stability and moves your center of buoyancy sideways. And again, now we can see that we have increased the G set quite a lot compared to the original boat we started from. But let's see if there are other approaches that we can look at. Now, on a laser dinghy like this, the crew, the person sailing this boat, probably weighs approximately the same as the boat, or even more. And the combined boat and crew weight is what pushes you down, and the buoyancy brings you up. And that's about moving the center of gravity laterally and sideways. And by hiking out, you balance the boat. So that could also be incorporated in sailboat design, couldn't it? Lots of sailors use their boat both for cruising and racing, and they do exactly as the laser. They put people on the rail, and you should actually invite your heaviest friends to sit on the rail, because that will have the biggest impact on moving your center of gravity sideways and thus giving you a greater G set. And if you're really keen, you can actually start moving some of your sails and other loose equipment up to the windward side. That will also help. So, but that really doesn't impact the boat as such and its stability. But there are some boats that at least can give you water ballast tanks. Special cruising boats, I'd say, where you can replace the people on the rail with a water ballast tank. And that would then again be a design feature of the boat with the same effect. But if we really want to improve stability further now and move into the racing arena, canting keels come up. And canting keels means that you have big hydraulic cylinders, which means that you can shift the keel over from one side to the other, because you get more effect out of having the keel out to the side, the bulb, and moving the center of gravity laterally that way rather than having it far down. So by moving it out like this, you have a much bigger effect. But of course, then the other purpose of the keel is to prevent leeway. And if you have a canting keel like this, you will need dagger boards or extra keels that you can then move up and down. But you see, so far we've been talking about static stability. That means that we've been playing around with the center of gravity and the center of buoyancy. And it really doesn't matter whether the boat moves or not. But of course, if we can use the boat's speed through the water to generate forces, that opens for new possibilities, and that's what we do with foils. As I believe most of you have seen, these asymmetric foils have been introduced on the most extreme racing boats, such as the Imoca 60s, the Mini Transats, and so forth. So they don't only provide significantly increased righting moment, these foils, but they also lift the boat much higher, even out of the water. The latest generations almost fly entirely of even monohulls. And of course, this gives speeds that are totally unheard of for other boats. But it's sort of impractical for the cruising sailor. And of course, such solutions are enormously expensive, but my God, they are fascinating. And I know that I would really have enjoyed to spend a day on a boat like this, but probably they won't let me, considering my age. But the ideas we have here, are they totally useless for normal boats? There have been some interesting projects on normal boats like this by introducing what would you call a keel box just under the floorboards in the boat. And if you then insert an asymmetric foil in this one and pull it back and forth, well, you'd be able to generate lift, both lifting the boat a bit out of the water as well as giving a contribution to the righting moment. So the possibilities are there, and still you could have a livable interior. But talking of livable interior, no other boat can match a catamaran when it comes to livable space. And even some trimarans now come with a full flat on top of their three hulls, so they also provide ample space. Stability-wise, these are totally different animals from monohulls. A multi-hull will not have any weighted keels, but it will get all its stability from its beam. And the keels might therefore be very light, and it's very easy to make them retractable if you want to, but they will only serve to prevent leeway. The catamaran will, of course, have its displacement divided equally between the two hulls, whilst the trimaran usually have most of its displacement in the center hull, and the pontoons or the side hulls, they basically act as stability support. So how does stability work when they start healing, and what are their maximum G-sets? And the answer here is that the multi-hulls will have their maximum G-set just as the windward hulls or hull clears the water, meaning all the weight is taken by the leeward pontoon or hull. For a catamaran, that means that it will be heeling about 10 to 14 degrees at maximum G-set, whilst the trimaran probably will be at about 25 to 30. Now, that means actually that the maximum G-set is getting close to half the beam of the boat, especially for the catamaran. It doesn't heel that much at maximum G-set. Now, slightly smaller for the trimaran given trigonometry. But having said that, a trimaran is usually somewhat wider, so probably it's more or less same. Now, let's have a look at the G-set curves and compare it to a monohull. And here they are, all the three curves: trimaran, catamaran, monohull. I'm quite sure you remember the monohull with its maximum stability at around 50 to 60 degrees, and then an angle of vanishing stability around 120. And if we're talking about a 40-foot monohull, the G-set on a typical boat would be in the range of 70 centimeters. Then look at the striking difference to the multi-hulls, with the catamaran here already at 10 to 14 degrees with a G-set which is 4 times the maximum of the monohull. And that means that this boat is incredibly stable, and you will feel it the moment you're on board due to the motions of the boat. Now, in this picture, the trimaran is slightly under the cat, but that is simply because I have assumed them to be of the same beam. And as I said in the previous slide, usually trimarans are a bit wider than the cats, so it's more or less same. And then we remember that the righting moment equals G-set times the displacement. And for the monohull, that equaled that we put 2 cars on the rail of the monohull. Now, with 4 times the G-set, that makes 8 cars, just to give you an idea of the forces of and the size of this moment. Now, this immense stability comes with some challenges. And if you have a light multi-hull, and again, righting moment is G-set times the displacement, and if the displacement is low, then of course the righting moment goes down as well. So then capsizing is an issue. And if you start flying the hulls and you come up here, it falls pretty rapidly down here. So here you have to be careful. But for the heavy multi-hulls, and that would be catamarans, because those are the ones which are the cruisers, they will be so heavy that the forces will be so great that you'll probably lose your mast long before you'll be flying a hull. So that's the problem there. You have to reef by the numbers to make sure you don't damage the boat. As we have seen from the G-set curves, it's absolutely possible for a multi-hull to capsize by wind alone, but that is not that easy for a monohull. Now, as the boat heels over, the projected area will be less and less, so that there won't be any wind forces left actually at 90 degrees heel, but you'll still have lots of positive stability, at least if the boat is approved to the EU RCD Category A. So to capsize a monohull, you would need a breaking wave. Now, this breaking wave transfers energy to the boat, because it's not just a matter of forces, because we need to transfer forces through a certain period of time to accelerate the boat and actually turn it around, meaning that's an amount of energy that has to be transferred. And the energy needed is given by the area under the G-set curve. And here we've got one blue curve and we've got a red curve, and there's one place where it's overlapping. And we see that the remaining blue part is bigger than the remaining red part, meaning that there's actually more energy required to capsize a multi-hull than a monohull. Well, if you're out sailing in the ocean and you get into a storm, you might, of course, ask, how big wave is required to roll over my boat? Very valid question. And I looked into Heavy Weather Sailing, a book by Peter Bruce, I can really recommend that. If you haven't read it already, you should put it on your list. And he again pointed to some model tests performed by the Wolfson unit. And those model tests showed that a lightweight, modern, wide, fin keel yacht could be rolled over by a breaking wave with a height of only 35% of the boat length, provided you were lying beam on, taking it directly on the side. And then we have those breaking waves. If you look at the pictures from the model test here, these are really short and steep waves, and you really find that type of waves in the ocean. Those would be more typical for shallow areas and often in combination with heavy currents. But the good thing with the model test, they proved that if you used an adequate brogue, keeping the stern into the wave, that required much higher waves, and actually they couldn't produce higher waves than 55% of the boat length. So with the drogue, you were safe at least till that limit. We're approaching the end of the video, but in the opening, I promised you that we should have a little look at the EU requirements, being the Recreational Craft Directive, also called RCD. And the RCD was implemented from 1998, and all new recreational craft sold in Europe after that date had to be certified to meet the requirements as given by this RCD. And this is a comprehensive set of regulation consisting of more than 100 standards, covering everything from strength to engines and engine emissions and electrical installations and gas installations and design of hatches and you name it. And of course, there is one on stability as well. All these requirements are also graded to meet different design categories depending on what conditions the boat will be sailing in. Will it be sailing on the open ocean, or will it be an inshore vessel? And in this respect, all those sailboats that we've been discussing in this video would be category A, meeting the toughest requirements. That means wind speeds above 20.8 meters per second and significant wave height of 4 meters plus. That really means maximum wave heights of 8 meters, meaning that we'll be out in the ocean. And that brings us to the fascinating and intriguing document ISO 12217-2, Small Craft Stability and Buoyancy Assessment and Categorization, Part 2. Now, this document contains all the things that we've been talking about, and one of the things it does is that it sets minimum requirements. Minimum requirements for angle of vanishing stability, that's when the G set is 0. Minimum requirements for the G-set curve area, which is then the energy which is needed to turn the boat. And then, of course, it also sets requirements for location of hatches and free surface effects so that we avoid the problems of water filling and flooding, which you remember was the biggest threat to stability. Taking a quick look at angle of vanishing stability as an example, we can here see the equation for that, which is then 130 minus 2% of the boat, which means that, for example, 10,000 boat in category A, then we'll have 130 minus 2% of 10,000, that will be 110. So here is the minimum requirement in that case. And then we have the stability index, or STIX. Now, if the boat is designed to minimum requirements only, that will probably be a pretty poor boat. So the STIX allows for some variations in this. So if you're weak on some points, you have to be strong on others. For example, down flooding is poor, then angle of vanishing stability has to be better. That is shown in this equation with two parts. One is connected to the length of the boat. A big boat is better in the ocean, we agree on that. And then you have several factors, and we'll look at these factors in a minute. And when most of these factors are close to 1, and you multiply them with each other, and then you take the square root of that, and you multiply it with the first thing here, and then you get the number for the sticks. And if you're in the A category, as we're talking about, that has to be at least 32. And here we have those factors, and all of them have their own equations for determining their value. And with some variation, these factors have maximum or minimum between 1.5 and 0.4. Now, let's take a quick look at them. Now, the first one, FDS, that is the factor for dynamic stability, which then addresses the area under the stability curve. And as we remember, that is about the energy required to capsize you. Then we have the inversion recovery factor, which addresses the boat's ability to righten itself, and that is connected to the angle of vanishing stability. And then we have another one, which is called knockdown recovery factor, looking at the boat's ability to recover after the boat's mast has been in the water and the sails have been filled. Of course, that gives some extra resistance, and that takes a look at the sail area and where the sails are positioned according to the hull and so forth. Then we have the displacement length factor, which is a factor that rewards heavy boats. And remember, G set times the weight of the boat, that gives the righting moment. So a factor rewarding heavier boats, that is sort of good. Then we have the beam displacement factor that looks at an hull shape and the increasing vulnerability to be knocked over if the beam and flare is large relative to the boat's weight. So that's again the flat boats we're punishing a bit here. And then we have a wind factor moment, which calculates the risk of flooding if you're knocked down by a gust. And of course, down flooding in general, looking at the angle of heel you must reach before ingress occurs. So these are the factors. And if we go back to the sticks, you will now understand how this sort of controls the whole stability thing, so that minimum requirements alone are not enough, and thus ensuring a safe boat for you. Let's conclude this video with a recap. Stability is determined by the center of gravity of the boat and the geometry of the boat. And in this context, the horizontal distance between the buoyancy working upwards and the weight working downwards gives a righting arm G set. Now, since the righting moment Rm equals G set times the weight of the boat, a heavy boat will give greater stability than a light boat. A wide boat improves the form stability by moving the center of buoyancy sideways and thus increasing the G set. And a heavy keel and or lighter sails and rig lowers the center of gravity, and this of course contributes to improved stability. The G-set curves describes the boat stability, with the angle of vanishing stability indicate when stability is lost. And the area under the G-set curves indicates how much energy is required to capsize a boat due to impact of steep breaking waves. And I have to say, through my entire life of sailing, with lots of storms, I have never been close. Water ingress and the free surface effect are the worst enemies of stability, and the ISO 12217 and the stability index gives the complete picture of the overall risk factors in stability. So if your boat is certified to category A, you will be safe. So now I hope that even if you experience things like this, you feel safe and hold on instead of wondering whether the boat will capsize, because it won't. Sail safely.